Assalamualaikum warahmatullahi wabarakatuh. I'm Muhammad Azrul Hisham bin Jusuf from Group J. Would like to present our project assignment for fluid mechanics 2. Our topic for this project is flow through the duct. Next, we go to group members. The fourth of us work together to complete this project assignment. I would like to introduce my group member, which is me, Muhammad Azrul Hisham, Iqbal, Daniel Musa, and Daniel Haika. Our leader for this project is Muhammad Iqbal. Next, we go to task allocation. For task allocation, our leader Iqbal distribute some parts to our members that contain in our project to complete this project. This is a task allocation, which is group introduction by me, Hazrul, introduction of flow through duct, Daniel Haika, theory, Daniel Haika, objective, me, detail of geometry and dimension, me, and method use, simulation by ANSYS Plum by Iqbal, and lastly, result explanation and theory related, which is Daniel Musa.
Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad Daniel Haikal bin Muhammad Syahril. Now I will present about introduction. Fluid is categorized into external or internal flow based on whether it is forced to flow over a wall or through a medium. Internal and external flow possess different characteristics. In flow through duct, we consider internal flow where the duct is completely filled with the fluid. The flow is primarily driven by a pressure difference. Liquid or gas flow through pipes or duct is commonly used in heating and cooling application and fluid distribution networks. In such cases, the fluid is commonly forced to flow through a flow section by a fan or pump. We focus on friction because it is directly related to pressure drop and head losses during flow through pipes and ducts. The pressure drop is then used to calculate the value of pumping power required. The term pipe, duct, and conduit are usually used interchangeably for flow sections. In general, circular cross-section flow are referred as pipe, especially when the fluid is a liquid, and non-circular cross-section flow are referred as ducts, especially when the fluid is a gas. Tubes are commonly used to describe small diameter pipe. Next, I will continue with theory. Although fluid flow theory is considerably well understood, theoretical solutions are only obtained for a few simple cases, such as fully developed laminar flow in a circular pipe. For most fluid flow problems, we must rely on experimental result and empirical relationship rather than closed-form analytical solution. Because of the non-slip condition, the fluid velocity in a pipe increases from zero at the wall to a maximum at the pipe center. It is easier to work with an average velocity in fluid flow because it remains constant in incompressible flow when the cross-sectional area of the pipe remains constant. The average velocity in heating and cooling application may change slightly due to change in density with temperature. In practice, however, we evaluate the fluid properties at some average temperature and treat them as constant. The convenience of working with constant properties usually outweighs the slight loss in accuracy. In addition, friction between fluid particles in a pipe causes a slight increase in fluid temperature as mechanical energy is converted to sensible thermal energy. However, the increase in the temperature caused by frictional heating is usually too small to be considered in calculation and is ignored. The value of the average velocity at certain streamwise cross-section is identified by the requirement that the conservation of mass principle is satisfied, where m dot denotes mass flow rate, r denotes density, ac denotes cross-sectional area, and ur denotes velocity profile. The average velocity of incompressible flow in a circular pipe with radius r is then expressed as equation below. As a result, if we know the flow rate or the velocity profile, we can easily calculate the average velocity. The flow pattern is described as laminar in the first scenario with smooth streamlines, and highly ordered motion, and turbulent in the second scenario with velocity fluctuation and highly disordered motion. The transition from laminar to turbulent flow does not happen all at once. Rather, it happens over a period of time when the flow transforms between laminar and turbulent flow before becoming fully turbulent. Reynolds number. The geometry, surface roughness, flow velocity, surface temperature, and type of fluid all influence the transition from laminar to turbulent flow. Osborne-Reynolds discovered that the flow pattern is determined by the ratio of inertial force to viscous force in the fluid, which after that it was named as Reynolds number and expressed as equation below, where V is the average flow velocity, D is the geometric length, and V is the fluid kinematic viscosity. The Reynolds number for flow through non-circular pipe is determined by the hydraulic diameter dH, which is defined as dH is equal to 4 SC over rho. The entrance region. Consider a uniformly flowing fluid entering a circular pipe. The fluid particle in the layer in contact with the pipe wall come to a complete stop due to the non-slip condition. This layer also causes the fluid particles in the adjacent layers to gradually slow down due to friction. To compensate the reduced velocity, the velocity of the fluid at the pipe's midsection must increase in order to maintain a constant mass flow rate through the pipe. As a result, along the pipe, a velocity gradient develops. The boundary layer is the region of the flow where the effects of viscous shearing force caused by fluid viscosity are felt. The flow in a pipe is separated into two regions by the hypothetical boundary surface. The boundary layer region where viscous effects and velocity change are significant, and the irrotational flow region where frictional effects are negligible and velocity remains essentially constant in the radial direction. The thickness of this boundary layer increases in the flow direction until it reaches the pipe center and thus fills the entire pipe, at which point the velocity becomes fully developed a little further downstream. The region between the pipe inlet and the point at which the velocity profile is fully developed is referred as the hydrodynamic entrance region, and the length of this region is referred as the hydrodynamic entry length. Flow in the entrance region is referred as hydrodynamic developing flow because this is where the velocity profile develops. The hydrodynamic fully developed region is the region beyond the entrance region where the velocity profile is fully developed and remains unchanged. When the normalized temperature profile remains unchanged, the flow is said to be fully developed. When the fluid in the pipe is not heated or cooled, hydrodynamic fully developed flow is equivalent to fully developed flow because the fluid temperature remains essentially constant throughout. Due to eddy motion and more vigorous mixing in the radial direction, the velocity profile in the fully developed region is parabolic in laminar flow and much flatter in turbulent flow. When the flow is fully developed, the time average velocity profile remain unchanged, and thus hydrodynamically fully developed is equal to delta U in bracket Rx over dx is equal to 0. The slope of the velocity profile at the surface is related to the shear stress at the pipe wall tau. Not only does the velocity profile remains constant in the hydrodynamic fully developed region, but so does the wall shear stress. Consider the flow of fluid in the pipe's hydrodynamic entrance region. The wall shear stress is greatest at the pipe inlet where the boundary layer thickness is smallest and gradually decrease to the fully developed value. As a result, the pressure drop is greater at the pipe entrance and the effects of the entrance region is always to raise the average friction factor for the entire pipe. This increase is significant for short pipes but insignificant for long pipes. Entry length. The hydrodynamic entry length is typically defined as the distance from the pipe entrance to where the wall shear stress is within about 2% of the fully developed value. In laminar flow, the non-dimensional hydrodynamic entry length is approximated as hydrodynamic length laminar over d is approximate to 0.05 Reynolds. The hydrodynamic entry length for Re is equal to 20 is approximately the diameter, but increase linearly with velocity, while the hydrodynamic entry length is 115D in the limiting laminar case of Reynolds number is equal to 2300. In turbulent flow, the intense mixing caused by random fluctuation usually overpowers the effects of molecular diffusion. The non-dimensional hydrodynamic entry length for turbulent flow is approximated as hydrodynamic length turbulent over D is equal to 1.359 Reynolds power of 1 over 4. In turbulent flow, the entry length is much shorter as expected and it is independence on the Reynolds number is weaker. Beyond a pipe length of about 10 diameters, the entrance effect become insignificant in many pipe flow of practical engineering interest, and the non-dimensional hydrodynamic entry length is approximated as hydrodynamic length turbulent over D is approximate to 10. Laminar flow in pipes. When Reynolds number is less than 2300, flow in pipes is laminar and the flow is fully developed if the pipe is sufficiently long that the entrance effect are negligible. In this section, we consider the steady laminar incompressible flow of fluid with constant properties in the fully developed region of a straight circular pipe. In the fully developed region of a straight circular pipe, we consider the steady, laminar, incompressible flow fluid with constant properties. The momentum equation is obtained by applying momentum balance to a differential volume element, and the velocity profile is obtained by solving it. Then we use it to derive a friction factor relation. One of the most important aspects of this analysis is that it is one of the few available for viscous flow. In fully developed laminar flow, each fluid particle moves at a constant axial velocity along a streamline and the velocity profile remains unchanged in the flow direction. There is no motion in the radial direction and thus the velocity component in the direction normal to the pipe axis is everywhere zero. There is no acceleration since the flow is steady and fully developed. Consider a ring-shaped differential volume element with radius r, thickness dr, and length dx that is oriented coaxially with the pipe. Because the volume element only involves pressure and viscous effects, the pressure and shear forces must balance each other. The pressure force acting on a submerged plane surface is equal to the product of the pressure at the surface centroid and the surface area. A force balance on the flow direction volume element gives as equation below, which indicate that the viscous and pressure force balance each other in fully developed flow in a horizontal pipe. Rearranging and dividing by 2 pi dr dx, we get the equation below. Then taking the limit as dr dx is equal to 0, give equation below. Then we substituting tau is equal to negative du dr dividing by r and taking mu constant give the desired equation. In pipe flow, the quantity du over dr is negative and the negative sign is included to obtain positive values for tau. The equation left side is a function of r and its right side is a function of x. And equality of the form fr is equal to gx can be satisfied only if both fr and gx are equal to the same constant. As a result, we conclude that dp over dx is constant. This is confirmed by performing a force balance on a volume element with radius r and thickness, which give dp over dx is equal to negative 2 tau w over r. Here, tau is constant since the viscosity and the velocity profile are constant in the fully developed region. Therefore, dp over dx is constant. Equation above is solved by rearranging and integrating it twice to give ur is equal to r square over 4 mu times dp over dx plus c1 ln r plus c2. Therefore, the velocity profile in fully developed laminar flow in a pipe is parabolic with a maximum at the center line and minimum at the pipe wall. Also, the axial velocity u is positive for any r, and thus the axial pressure gradient dp over dx must be negative. For example, pressure must decrease in the flow direction because of viscous effects. It takes pressure to push the fluid through pipe. The average velocity is determined from its definition by substituting equation and performing the integration, yielding like this below equation. Combining the last two equations, the velocity profile is rewritten as UR is equal to 2 V average times 1 minus R square over capital R square. Thank you.
Next, for objective of the project is first, identify typical value of Reynolds number for the laminar, transitional, and turbulent regime of flow in a duct with a circular cross-section. And then understand the friction concept, apply in pipe flow, and obtain the friction factor for different type of flows. Then measure the force generated by moving through a curved rectangular duct. And the last objective is test the validity of control volume analysis based on the linear momentum principle. Next, we go to other slide. This is the rectangular duct model from SolidWorks that have been given. From this model, our group will define its dimension and geometry. Also, make some analysis using ANSYS Fluent. The unit we choose to measure this model is centimeter. You can see the upper right corner, the overall view of rectangular duct. Assume the inlet and outlet. So the upper left corner is top view. The width of outer is 6 cm and the inner is 5 cm. So we know that the thickness from inner to outer is 0.5 cm. From view, we can see that all dimensions have been measured, include the radius of duct band. That's all for dimension detail and geometry. So the simulation of method Iqbal will conduct and show the step by using ANSYS Fluent.
Okay, this is ANSYS Workbench. Okay, to start the CFD analysis, choose Fluid Flow Fluent, double click on it. Okay, and then now we're going to insert the geometry. So right click on geometry, and then import geometry and browse the file. The file is in a step file format, and for this case, it's part 1. So open, and then right click again at geometry, and then edit geometry in space clamp. Okay, this is a space clamp. Okay, so click on prepare on the toolbar and then click on volume extract. Okay, choose this icon, and then we're gonna choose this type. Okay, and then we're gonna choose the another side. Okay, and then after choosing the both side, click complete. Okay, and then on this structure, untick the sweep thin tool, and then we can minimize the space clamp. Okay, and mesh, click on mesh, and then right click, then edit. Okay, now we're gonna start the meshing. We click on this plus symbol on the geometry, and then right click on FFF swept thin tool, and then right click, press the body. Okay, now click on the mesh, right click, insert and sizing. Okay, choose the first 4 edge of the first side. Okay, for example, on this side, we're going to choose the 4 edge. You can choose the 4 edge. Okay, 4, and then apply. And then for the type, change to number of divisions and change 1 to 50. Okay, now we're gonna do it again. Click on mesh, right click, insert and sizing. Okay, now we're gonna choose the another side. We still are going to choose 4 edge. So 1, 2, 3, 4, and then apply. And then type also change to number of division, 50, enter. Okay, now we're gonna generate the mesh. So generate the mesh. Okay, now we can see the mesh after we do the sizing method. Okay, now we're gonna improve the mesh. So we're gonna insert another type. Right click on the mesh, insert, and now we're gonna insert a inflation method. Okay, so for inflation method, just choose the whole body. Okay, apply. And then for the boundary, choose the first side and then the second side, then apply. Okay, now we're gonna generate the mesh. Okay, now we can see the mesh. Click on this mesh toggle bar, and we can see that now the meshing element is quite different from the previous one because this is the improved one. It's better. Okay, so we can see the quality. Okay, and then change the mesh metric to skewness, and you can see that by default the target skewness is 0.9, and now the maximum is 0.77929. Okay, now we're gonna define the inlet, outlet, and also the wall for the duct. Okay, so we're gonna just choose one side and then right click, and then go to create name selection, then name it as inlet, enter. Okay, now we're gonna choose the another side, right click, create name selection, and now we're gonna put outlet, enter. And now for the wall, just choose everything in the middle as a wall. So choose everything. We're gonna choose everything. Okay, this one, this one. Oh, sorry. This one, 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 and then okay, and last one. Okay, one or two more. Okay, so we have to choose all the wall, and now we're gonna right click and then create name selection, and we give it name as wall, and then enter. Okay, and we can see the name. Okay, this one we can just delete it. Okay, so we have inlet here, the right, in the left, outlet on the right, and wall for the wall in the middle. Okay, now we can just minimize the meshing, and then on mesh, right click on mesh, and then update upstream component, and then right click again, update mesh. Okay, now on setup, click on setup, right click and edit. Okay, on this flow launcher, you can click on double precision and then change the solver processes to 4, and then you can start. Okay, now this is a fluent. Okay, on the toolbar, click on domain check and then perform mesh check. And then on the physics toolbar, click on energy. And then on the left side, click on plus on the models, and then double click on viscose SSTK omega. And then we can see the all parameter here, and then click OK. Okay, then for the boundary condition, now we're gonna define the boundary condition. Okay, for the inlet, double click on inlet. Okay, I'm gonna change the, okay, first we're gonna change the unit first. So here units, and then you search for temperature. Okay, change it to Celsius. Okay, click list and then close. Okay, we're gonna choose inlet again. Now we're gonna define the temperature for the inlet as 16 degrees Celsius, and then for the velocity magnitude is 5, and then apply, close, and then for the wall, then double click on wall. Okay, for the, now we're gonna define the thermal temperature, change the temperature to 30 degrees Celsius, and then apply, and then close. Okay, now we're gonna do the initialization. Okay, double click on initialize. Okay, next we're gonna run a calculation. So double click on run calculation. Change the number of iteration to 200, and then we're gonna check the case. Okay, no recommendation to make at this time. Okay, now we're gonna do the calculate. So double click on calculate, and now it's gonna calculate. Now the calculation is complete. So you can minimize the fluent and then we're going to check the result. So right click on result and then edit. Okay, this is a CFD post where we can see the result for our CFD analysis. Okay, now we're gonna insert a counter. So from the toolbar, click on this icon, which is a counter, and then name the counter one. Okay, and then for the location, we're gonna choose inlet, outlet, and also the wall. Okay, click OK, and then we can apply. Okay, so here is the counter for the pressure. The variable is pressure. Okay, now we're gonna untick it and we're gonna insert another counter. So now we're gonna location is still the same, inlet, outlet, and also the wall. Okay, but the variable we're gonna change it to temperature. Okay, apply. Okay, now we can see the counter for the temperature of the duct. Okay, now we're gonna take counter 2 and we're gonna insert a volume rendering on this icon. Volume rendering 1, okay. And then on the geometry, the variable is pressure, and then we're gonna apply texture. The texture is white metal, and then apply. So this is the counter for the pressure of volume rendering. And now we're gonna insert another one more, volume rendering 2, but now we're gonna change it to temperature. Okay, so same as before, apply texture and then white metal. Okay, apply. So this is the counter for the temperature volume rendering 2.
The simulation is represented in a color coding manner, where blue is the colder region and red is a hot region. Whereas for the pressure region, the blue indicates a very low pressure and red indicates high pressure. For this simulation, there are two results that are produced. The first is temperature. As heat is applied on the outside wall, high spots are observed throughout the duct. They are formed only on sharp corners on the wall. Low temperature area are in the middle of the duct. As we can observe, there are variation in temperature. This is formed due to the moving air inside of the duct. The high temperature spots indicate a low velocity fluid area, likely due to formation of boundary area on the surface. Next is the result for pressure. As the fluid flows from high pressure area towards the low pressure area, we can see that near the inlet area, the pressure is higher, and on the bend, the pressure is the maximum on the heating surface and minimum on the dragging surface. On the inner side of the curve, the pressure is negative. This in turn pulls in the fluid to move away from the high pressure area. After the curves, the pressure regulates itself to a slightly negative pressure, allowing the fluid to flow out from the outlet. According to the entry length theory, the longer the duct length is, the closer it gets to a laminar flow, whereas if it's a shorter one, it is a turbulent flow. This is also true in our simulation. As we can see, A velocity profile can be observed near the inlet area as the profile transitions into a fully developed velocity profile. This is true according to the theory of the entrance region.